All right, let's get started then. So, what my talk is about today, and what I hope to demonstrate to you guys, is not just the benefit of open data as data itself, but really building on top of the data to make something more valuable and to assist with land use planning decisions and emergency evacuation decisions and all these other actual practical outcomes that can be realized by using open data. So we're more focused on the down the chain benefits of what can come out of releasing this data and making it public. So as Giovanni mentioned, my background is as an environmental engineer, as a civil engineer. I used to design roads and highways and property developments, and specifically manage the impact of flooding on those things. Following on from that, I got involved in open data and specifically GeoNode, and these days I write software to help us solve flood management problems using open data. And that's what I'll talk you guys through today. So this is kind of the outcome that we're looking to achieve, just to give you a concept of the big picture. This is a web browser, and it has interactive, viewable, shareable flood models straight through a web page. So that's kind of the end target that we're looking at aiming for, and the benefit of having this stuff in the web as opposed to a PDF document. We'll go through that in a bit later, but it opens up some really neat ways to manage data and manage flooding. Now, of course, we're just talking about flooding today. The same philosophies and the same principles apply to most environmental problems. They could be traffic management. We could be talking about sewage and water supply. We could be talking about bushfire risk. The point isn't necessarily to go deep dive into the flooding aspect. It's to demonstrate what's possible using open data. So I'm not going to train you in how to build flood models, and the flood model that we build today will be much too quick and around the edges to be genuinely useful, but the point that I want to show you is how we can do that collaboratively together. So what we're going to do is download some open data LiDAR from the Hydrata site, which I understand you guys have already touched on today. Then we're going to apply some rainfall onto that LiDAR terrain and calculate some flood maps based on that rainfall. We'll bring in some building footprints from the mapathon that Jess was running today. And then we're going to look at an exercise where someone's proposing a new road across the floodplain, and we will recalculate our model to take into account that new road and try and see what kind of impact this new road is going to have on the buildings that we mapped. Now, it's a reasonably ambitious agenda, so I'll dive straight into it and I'll move reasonably quickly. And Giovanni, I guess you can shout out if there's any questions or you need to slow down, but I'll just get straight into it. So I'm going to create a new project here. I'll call it Understanding Risk. Now all of this is available on the hydrata.com site. I'll run through that in a minute, but just for time's sake, you guys have all seen the Hydrata site today. So I'm going to download this particular area straight from Hydrata as we talk. So while that's downloading, Hydrata is built on GeoNode the same way Hydrata is built on GeoNode. We use it as a content management system to manage the inputs and outputs of the hydraulic modeling process, and GeoNode works really well in that respect to keep track of all the data. Okay, let me make sure I get the right one. Yeah. So now that I've downloaded that data, I'm going to upload it to Hydrata. I don't think that actually undid. Okay, as that's uploading from my desktop up into Hydrata, yeah, I'll talk a little bit about the benefits. Traditionally, with a flood study, you go and hire an engineering consultant. And they produce this fancy flood study, which has got hundreds of thousands of dollars worth of work in it sometimes, stored in a PDF document, or these days more often static GIS files. But at the end of the day, when you come try and update this thing, it's you have to re-engage the same consultant and pay them more money, and the whole thing just tends to depreciate in value over time rather than getting more valuable. So what we're trying to do by putting this data online is that when someone goes out and contributes significant engineering input and goes and does things like mapping houses and finding culverts and bridges and understanding the terrain, all this data is stored online in the public or private cloud, depending on whether you want to use your own data center or Amazon's data center or wherever it needs to be. But the point is, it's not on someone's desktop in an office somewhere. So the same way as with OpenStreetMap, we can update and edit online the flood models, track changes and history, and build on the work that has been done by others in the past. So over time, the flood model gets more valuable rather than becoming out of date. So that's the basic concept and the outcome that we're aiming for. Now, this LiDAR is almost been processed. Should I wait for it? While the LiDAR's waiting, I'll touch on the next aspect that we're going to need, and that's rainfall data. So in this case, I've just prepared a short Excel file that has a 2-hour rainfall storm that starts out reasonably slow and then peaks at a high intensity of 250 millimeters an hour, which is enough to generate some pretty significant flooding anywhere in the world, and then back down to zero to let the catchment run dry. So this is the rainfall data that we're going to put onto our terrain. There we go, the layer's successfully uploaded now. So I'll open up this map. So we've trained GeoNode to do a bunch of fancy pre-processing for us. So it takes that LiDAR data that you saw on Haiti data, and it'll color code it and put it in the right spot in the world and make it generally easy to use and nice to look out for. But the first thing that we're going to need for our flood model is a flooding extent, and I'm just going to call this one overview. So this will be the boundaries of our flood model calculation. We have to specify a space on the planet where we want this numerical calculation to actually occur, and that's what we get with the flood boundary here. So now that I've created that layer, I'm just going to delineate our area of interest, and we're just going to look at a small little watershed here. Typically these, I'll call that exterior. Like I said, I'm not going to teach you all flood modeling, but you'll have to take some of it for granted. Just for context, I'll zoom out a bit here. So those who know their way around Port-au-Prince can get a feeling. This is quite a small model in the scheme of Haiti, but we want to have something that can run reasonably quickly and easily in a workshop environment. Typically this thing would be much larger, and you can cover large chunks of the country running these things, but they take 24 to 48 hours, I guess. So now that we have our model extents, let's add some rainfall. So this time series, I'm going to call it a 100-year storm for 2 hours duration. I don't actually know if it is that. Like I said, don't quote me on the rainfall. And then I just cut and paste that data from Excel into the model. And that happens to be in millimeters per hour. So there's our rainfall. And now I need a spatial component to that rainfall as well. So I'm going to apply it in a uniform manner over our area of interest here. Now, when you're doing a full-blown flood study, you'd often run many different rainfall events and many different scenarios. But for the sake of this thing, we're just keeping it simple, and I'll just run one so we can see what's going on. Okay, there's our rainfall, and I'm just going to apply it over our area of interest. If this was a big area, we'd have different intensities of rainfall in different parts. For example, the mountains often have much higher intensity, and then the flat areas will have lower intensity. So we could distribute this rainfall in a non-uniform way, but for now I'm just going to apply it like this. Okay, so there's our rainfall all set up on our terrain. Now, I know you guys were doing the OpenStreetMap Mapathon exercise. For the sake of time, I'm not going to import that full data set right now, but we could, and I can show you the work that you did earlier at the end if we have time. But for simplicity's sake, I'll just go ahead and quickly draw a few buildings of interest straight into Hydrata. But obviously the preference, if you've got the time and the discipline, is to import these building footprints from OpenStreetMap instead. But just bear with me while I create some buildings. Call that one 2. I'm sure the OpenStreetMap interface is much more effective at creating buildings than this one too. And you guys are probably better at drawing squares than I am, because those buildings are a bit wonky, but you get the idea. Okay, so now we've got some buildings mapped, we've got our rainfall. We need to actually run the simulation. So let's create a scenario, and I'm going to call this one the existing situation, which is basically what is there, current terrain, buildings, etc. And as for this particular simulation, I'm going to select the elevation that we just downloaded, our boundary we just created. I'll put the structures in, apply the uniform rainfall. There's a few other features that we could be using, but I won't for the sake of time. We'll run this model on a 30-meter squared triangle grid, and we're going to output something every minute, and we're going to run it for 2 hours in the real world, which I promise will not take 2 hours in the demonstration world, because it's Friday afternoon. Okay, so we've got our model set up, and I'm going to start running that. Okay, so that's loading and off and calculating. Now, while that's happening, let's go ahead and pretend that we're now the planning department for this area, and we've got a scenario where there's someone up here on the hill who wants a road built to his house. I don't really know why or how, but for some reason this chap needs this road extended up there. I'm just creating a scenario that should demonstrate through way of a little story what could possibly typically happen within a planning department. So this guy's decided that this is the path for his road. There's a nice new alignment. Now, what we're going to do is look at running another scenario, and we're going to call this proposed road. We'll keep everything else the same, except now, of course, we're using our new structures. So you can see here that model run took 1.5 minutes to run, and it keeps a track of all the different hydraulic and physical variables that have gone into that model scenario here. We can manage through the dashboard. For the more technically inclined, the model that we just ran is actually written in Python. It's an open source flood model. Goes by the name of Anuga. If any of you have had experience with flood modeling, you might have also seen software like HECRAS, which is run by the US Army Corps of Engineers, or more commercial codes like 2Flow or Mike2D. This is Anuga is an open source version that solves the similar set of equations. It doesn't come with a fancy user interface, but because it's open source in Python, we can integrate it into products.
Sorry, David, can you full screen the presentation?
Sorry? Full screen it?
Full screen the presentation.
Yeah, okay.
No. From the right corner.
There we go.
Yes. Thank you.
Where was I? Yeah. So this one doesn't come with a lot of the fancy graphical user interfaces and tools that the commercial codes come with, but the fact that it's open source and the fact that it's Python mean that we can integrate it into the platform like this. So this log file that you can access through here is a log file of that Python code that's run while we were waiting. Now, if all has gone according to plan, that one's completed, so let's set the second one off. Now, this existing scenario, let's have a look at the results that we've produced. Okay, so you can see here, up the top of the watershed, we've got shallow flow coming down from the hills, and it's starting to accumulate in this valley, and then it's flowing down here and joining in with a another river here, and then spreading out across the developed area and interacting with the road and the houses here. So this is our existing situation with the flooding, and you can see this new road, which wasn't in that calculation, but you can see that this new road to this house up on the hill is potentially going to cause us some problems, because it's cutting right across that flow path that we weren't really aware of when we first proposed that road. To give you a bit of an example of what we can interrogate the depth here of the flooding at this particular location. It's 1.4 meters. And what can also be of interest for us is the velocity. So in this case, we're mapping the velocity of the water. We're presenting the results of the same calculation, except we're presenting the velocity results instead of the depth results. Now, this is important when you're planning things like flood evacuation routes, or dealing with problems like erosion or scour in the river, or designing works that need to withstand the force of the water. It's often the velocity that causes the problem. So mapping like this can help identify, for example, properties that are at risk of high velocity, where this velocity is coming down here, and the properties in the flow path here are ones that you might want to invest some time and money into providing a bit more protection, or perhaps relocating, or somehow managing the risk to these individual properties. So that's a general overview of the benefits of velocity mapping. Our proposed simulation is now just processing. What else can I show you? Over here, if we look at the depth result again, you'll notice that the ponding around these buildings is not particularly bad. Every flood event's going to have some form of dampness everywhere, and these guys, under the current situation, they're doing okay. All right, now that's completed our proposed scenario. So let's bring up the results of that. Okay, so here you can see the same water is flowing down here, except when it gets to our new road, and in this case we haven't allowed for an adequate bridge or designed a proper culvert in this situation. Now you can see the water is being effectively diverted off down this flow path, and it's impacting these 4 houses in a much more significant way than previously. The maximum depth here now is 200 mil, which is enough to go through a house and damage carpets and this sort of thing. So that gives you an example of how this infrastructure can be assessed, but to really understand the difference of what's going on and design effective mitigation measures, what we'd really like to do is compare these 2 scenarios. So what I'll do is actually subtract one flood surface from another. So we'll take the existing scenario and we'll compare it with the proposed road. And what we should come up with is a difference map, which will effectively show the impact that this proposed road would have on flooding in this location. And this is the kind of thing that will enable consultation with everyone who might be impacted by it, and hopefully enable the design of effective mitigation measures. When you can understand the risk that you're creating, then you can also use that understanding to design the mitigation measures. So let's see how this is going. Not yet. All right, so here we go. So what this has done is calculate the difference between those 2 model runs that we just ran. And you can see there's a lot of little tiny bits of noise where things aren't exactly the same. But where it gets really interesting is now we can see this road is diverting a lot of water to the west, which is solving the flooding problem down here for these properties. This particular property is now experiencing 100 millimeters less flooding than previously, but the road itself is creating flooding problems at these 4 properties. So when we have mapping like this, we can really work effectively to, in this case, the solution would be to size a culvert or a bridge under the road at this location, and try and keep the flow paths, match them back up to how they were before we started designing this kind of infrastructure. So that's essentially it for how we come up with, we take a bit of open rainfall data and we take a bit of open LiDAR data, we run it through some open source software, and hopefully come up with a really neat way of explaining to all stakeholders on this particular project what the impact of what they're proposing is in quite a quick and easy and collaborative manner.
Okay, David.
Okay.
Do you have something else to show?
Well, this was the question for you, Giovanni. There's a bit of technical stuff in here. If you want to go into it, we can. Otherwise, I'm happy to share the slides. Might be faster if you guys are on Friday afternoon and are looking to save a bit of time.
Okay, so yes, please send I'm going to upload all the presentations on a OneDrive folder with all the presentations. And so, yes, please. Okay, you already sent me a version. So if this is updated, share it with me.
Yep.
And so I will put on this OneDrive folder. So, okay, we are in the 30 minutes perfect. You went seriously perfectly into our time slot. So you adjusted all my mistakes actually today. Thank you
awesome.
very much in time management. But I will just get 10 more minutes of your time to have a round of questions. Yes, that's it.
There we go.
I model on, yes, we have one. Okay, can you hear the mic? Like, can you hear me now?
I can hear the mic, yes.
Okay. So yeah, so can you do the same analysis for storm surge for waves?
Yes.
Nice area, sorry.
Yes, so the same, the same model equations that solve the shallow water equations that we used just there, we can use them to model storm surge, we can use them to model tsunamis, we can use them to model sediment transport. Yes. And because everything is open source Python, if it doesn't have the right inputs or outputs, we just add them in.
Okay, there is a French question. I will translate.
Sur Hydrata, on retrouve le modèle de Lab, mais aussi des données sur les précipitations. Est-ce que simplement à partir de Hydrata, on peut entrer sur le logiciel ou on fait des simulations, une simulation d'utilisation?
Okay, I might reply to this question, but so engineer Leger, so he works for the Asian government, so asked that on any data we can find LiDAR models, we can find precipitation models. So if it's possible with this data to do the same model you are doing, so it's not possible to do all data because even though both are geonodes, Hydrata is a version of genome that is being customized to run short code. So what you can do is what you can download the data from Hydrata and then upload them on Hydrata, and they showed us an upload model. But we afterwards a private conversation with David to bring it over in a evening. Let's see. So, David, am I right? Did I reply well to the question?
Yeah, exactly. The GeoNode essentially just provides the engine underneath, and then we build stuff on top of that.
Okay. So, closing submission. Okay. Other question.
Thank you for this presentation. I think it's very relevant for the governments that are attending the conference to inform the planning of their infrastructure. I was very interested in your impact assessment and see how the construction of a road or infrastructure can affect the flood risk model. And I wanted to know whether other types of interventions that are not infrastructure would also be possible to be assessed as impacts into the platform. For example.
Hello? I just dropped out for a second. You can hear me again now?
Yes, we can hear you.
Yeah.
But did you hear the question?
Okay, yes, I did hear the question. So, yeah, we can assess. So the answer comes down to the inputs and the sensitivity of the actual hydraulic model. Now, you can put whatever you want into a model and get whatever you want out. To actually get sensible answers out, you have to have good on-the-ground data. So to assess a road we usually have pretty good data about how high it's going to be, how wide it's going to be, the location of it. If you're assessing things like deforestation of a hilltop or something like that, you're probably going to have to go out and collect hard, specific data about that particular impact. If you're collecting data about other management measures like stormwater detention or retention, which is the concept of building various ponds and dams throughout a watershed to capture the water and slow it down and reduce flooding. This sort of thing, because it's a physical asset, a physical infrastructure that we can measure, either a design or the real thing, then yes, that will be modelled quite effectively, and we'll be able to determine the outcome of that quite precisely. That's I can hear you now, not before.
Okay. I don't know if there are documents on your Kindle that specify assumptions or any technical information as to what's required for this a more precise protocol.
Sorry, I'm still getting a lot of echo in the microphone. I couldn't hear the question properly.
So the question is if there is a way to have the data implementation about the fault model and assumption to improve it. I don't know if there are any documents that go into the details of the assumption of the model. Like little things like this. Okay. Yes.
Yep. Okay, so the short answer for this particular model is no, we just built it then. I would need to write those things. One of the key aspects is that this doesn't replace the need for qualified and sensible engineering and qualified and sensible engineer to be hired and to go ahead and write that report with all the assumptions. Yeah, so I guess my point is, just because this is easy and accessible to use doesn't make it doesn't replace the need to have qualified, experienced professionals produce reports about the assumptions and the methodologies. Those things still have to be done. Yep.
Of course, it gives you an overview of what is like a rainfall was like one of the. Okay, so I think we. Okay.
So I'm sorry, but towards the end of the presentation, I got a bit lost. So you had the road and you have this red data and this green data.
Yep.
So my question is, was the green data like after placing a box culvert? And if not, is it possible to model if you install a box culvert? Is it possible to model the benefits of it?
Yeah, sorry. So I got most of the question about the red and the green data.
Yeah, I was confused about the red data and the green data where.
Yeah. Okay.
So if the green data was after installing a box culvert.
Yeah. So.
You mentioned that exactly that it will
So the green data shows you the area where the flooding has been reduced by the road, and the red mapping shows you the area where the flooding is increased by the road. In this particular situation, we did not design any culvert or any bridge under the road. So we're making a big impact in the red area, and we're creating a big positive impact in the green area. But in the next step, if we had time and effort and budget, would be to go ahead and design that box culvert and try and minimize both the green and the red area, so that we weren't changing the flow regime as drastically as we are. I think this map shows how drastically the road would change the flood regime if we didn't provide adequate mitigation measures like bridges or culverts. Does that make sense?
Yes, that's perfect. Okay, so then, thank you very much. I just want to tell everybody that today is 15 to midnight. See you bye. So thank you very much for waiting for us, and I don't know, I will share your contacts with everybody. If someone has a question, we forward it to you. And a big round of applause for
Thank you, everyone. And yeah, it'd be great to hear from you with your thoughts and feedback. And we love to learn from what you think, whether it's positive or negative, what the risks and what the rewards are of this sort of thing. So do get in contact. If you haven't got my email address already, Giovanni can pass it on to you. Thank you very much, and enjoy Barbados.
Bye.
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 Bye. See you, Jess.